earlier we have been drawing on the EasyEDA environment. So in this EasyEDA, we were drawing a simple diagram about how to connect the ambient light sensor in a circuit. So we have the microcontroller, sorry, not the ambient light sensor, but the display unit. So we have the microcontroller and then an OLED display unit with a certain interface. And we had to look from the resource center that how the display would be connected to our microcontroller project. And we had a look that, okay, it is with the SPI interface, and there are the certain pins with the pin names referring to the function of the pin. So chip select, master out, slave in, that's not connected. That's a clock signal, ground, operating voltage, and so on. And then the pin names here. We draw a circuit diagram with the connector for that one. And then today we continue with the similar exercise. We continue now, we study first that what is an ambient light sensor. So there is an ambient light sensor. There is a photodiode on that sensor unit. It's a small like 2 centimeters times 2 centimeters board with 6-pin connector. And also from that one, there is a more detailed description. And in the detailed description, there is again the description of the pins. And then we will also have a look at how to work with an acceleration sensor. So there is an acceleration sensor. The acceleration sensor itself is the small integrated circuit in here. And then the bigger part of the board is the connector. So, and then this acceleration sensor is connected again with 12 bits. But we will first start with the easier one with the ambient light sensor. So we need to know that how to connect the ambient light sensor. Okay, we could simply follow this instruction that, okay, connect the master in, slave out, the clock, ground, operating voltage. We will do like that. We will draw a circuit here, that a connector where we can like connect this module. But we can also have a look in detail at how it is working. And for that, they don't actually publish the schematic diagram of this module. So we can just have a look at in detail that. No, I would like to have a look on detail on that picture. Yep. So what there is the ambient light sensor itself is a photodiode, and then the circuit is very simple. There is one resistor, a capacitor, and one integrated circuit, and nothing else. That's the module. And then if we would like to have a study that how it is connected, we could actually follow the strips on the printed circuit board and see that how it is connected. But they publish the information of what is the integrated circuit here. The integrated circuit is an analog to digital converter. And that's made by the company Texas Instruments, which is one of the largest integrated chip manufacturer in the world. So the integrated chip there is a single channel 50 to 200 kilo samples per second, 8-bit analog to digital converter. Analog to digital converter means that it is taking the voltage. Somehow this the ambient light sensor is creating a voltage, and then it is converted to a digital number. We will briefly have a look at how a photodiode is operating, and that we can study, for example, just take almost any document about the photodiodes, and they have a similar explanation, of course, about the operating principle. But then also there are a few options how to build an amplifier for a photodiode. And then this is an amplifier circuit. So there is an operational amplifier, and an operational amplifier is a device that if you you can think about it as an amplifier where there is a very large amplification of the difference of these input voltages. And then the output goes to a voltage where the current through this resistor creates a voltage over the resistor, so that there is the output voltage on that side. And then this point here is in a 0 volt voltage, because the other point of the amplifier, this other input, is also in a 0 volt typically. And then with the photodiode, the circuit works in a way that the photodiode is actually creating a current when the light is hitting the diode. So there is a diode here, drawn in here. This is the photodiode. So the light is hitting the photodiode and it's creating a current. And normally a diode is a device where the current is flowing in that direction. So through the diode. But in a photodiode, it's a little bit different. When the light is hitting the photodiode, it is creating the current in an opposite direction. So there is this diode, photodiode, is creating a current which is flowing in this direction. And that's some microamperes. So this is drawn here as an circuit model of a photodiode. So there is this is the current source, and this is the current flowing in this direction. But there is no current source here, no capacitor, no resistor. Everything is just this circuit is describing how this photodiode is working. And then when the light hits the photodiode, it is creating a current in that direction. And the current, it can't take from the amplifier input. It's a high impedance input. The current doesn't flow into the amplifier or out from the amplifier, but the current is flowing. Then the only way where to get the current is from this line. And then the current is flowing through this resistor. And when you get some microamperes of current in here, and you put 100 of kilo ohm of resistor in here, and you get the microamperes flowing through that one, you get the voltage in the output. So when you get the current in here, you actually get the voltage in the output in here. And this voltage you could measure, for example, with the analog to digital converter. So you can measure the output voltage from here. The capacitor here is for defining that how fast transients this photodiode is detecting. The photodiodes are used, for example, on an communication technology. So in receivers of the fiber optics channels. So when you have a fiber optic link in a data communication, the receiver is quite often a photodiode. And then you put a really small capacitor here, and you get the fast changing bits of the transmission through this amplification and through the input of the next circuit. But if you are measuring something like just a light in a room, and you do not like to take the flickering of the lamps into the measurement so that you get a stable value out of the measured light input, you put here a large capacitor, and then you get a stable output out of here. So with this capacitor, you define how well it is detecting the very fast changes of the light intensity, like it is needed in data communications. So it is nanoseconds of duration of the pulses there of the light. And then this is really small capacitor in here. But if you try to avoid the 100 Hertz or 50 Hertz flickering of the lamps, you put a large capacitor here, and then you still get a stable output from here. So that's how a photodiode circuit is working. So a photodiode in here, and you get a small current, and you measure the current flows through a resistor, and then you measure that what is the voltage in the other side. So also in this circuit that we have the photodiode in here, we can see that there is the just a second. So the right circuit, so this one is the photodiode with the photodiode, the ambient light sensor. So there is the photodiode, there is the resistor, and then there are two capacitors to stabilize the voltages. And actually, we measure the voltage over the resistor directly with an analog to digital converter. So you create, by hitting the light, hitting the photodiode here is creating a few microampere current. And that few microamperes goes through a rather large resistor. And then we measure that what is the voltage over this resistor, and we measure the voltage with an analog to digital converter. That's the simple circuit in here. And then what we get out of the analog to digital converter is a digital number, so a binary number, which goes then through from the sensor data out. It goes to the microcontroller. And then this circuit in here is the type of the circuit is defined in here, ADC081SO21. And then we have a look on the data sheet of that one. So this analog to digital converter. And then this analog to digital converter, it's good for our purposes. With the operating voltage 2.7 volts to 5.25 volts. So it works quite well with our 3.3 volt circuits. And then it's easy to interface because with the microcontroller, it doesn't need any parameters in here. So we don't need to send anything from the microcontroller. We just connect it into the power and connect the voltage we would like to measure. So the voltage in here. And then we get the serial data out for the serial data, it needs a clock signal and it needs a SIP select. So these are for the microcontroller. This is the SPI interface on the microcontroller. So in the SPI interface, there is a clock signal, there is the data line. So this time it is the slave out master in data line. And then there is a SIP select where the microcontroller is telling to the chip that now I would like to discuss with exactly with this chip. And then what comes out of there, we will go further in the document and have a look at how the data looks like, which is coming out of there. So you can have different options of this converter, either with 8 bits, with 10, wasn't it? You have options. No, this is always with an 8-bit. So this is always with 8-bit accuracy. So what you get out of there, you get information like this. This is about how it looks like on the serial communications. So we can read it like this. We draw the SIP select pin down. With the microcontroller, it is drawing the SIP select pin down from 3.3 volts to 0 volts. Then, and the clock pulse goes to the chip. And this is the data line. When the SIP select goes down, there is 3 leading 0 bits. So first comes 3 0 bits, and then comes the bit data 7 up to data 0. These are the 8 data bits, starting from the most significant bit. And then comes 4 further zeros, just to fill in the communication that it is 16 bits. Because you communicate either with 8 bits or with 16 bits in the SPI interface. So you are filling the memory of the microcontroller, and the memory is referred always with 8 bits. So you get an 8-bit and an 8-bit information in there. But from that 8-bit information, we need to somehow get the bits out from the center, because these data bits are there in the center. So first comes the leading zeros, and then in the end there are the trailing zeros, and the 8 bits are in the middle in here. So that we need to then sort out in our code, that we take the 4 bits from the other 8-bit data and the 4 bits out of the other 8-bit data. We will have a look later on how this is done in the code. And now when we know the details of how this is working, I mean, what comes out from the analog to digital converter. So this chip, that one. Now we know also that what comes out from this serial data out line in this module. And it's time to make a drawing that how this module is connected into our microcontroller.